Hello friends, so here we are in our 8.7 notes. This is day 2 of solving. So a little bit more challenging, not for all of the problems. There is just another method of solving, and then a lot of them are kind of some hidden factoring within solving these logs and exponentials. So in day 1 of solving in 8.6, we talked about kind of two methods of solving. One is if you can get a log with the same base equaling each other on both sides, therefore you can just set those arguments to the same. Or if it's exponentials, if your bases can be rewritten as the same thing, then you can just set those exponents equal to each other. Well, what happens when you can't make your bases the same thing? Like example 1, there's no way that we can rewrite the 2 nor the 3 so that they're the same base of each other. So what we do for these case scenarios is we actually take the log of both sides. Remember, log is an operation. It's not a number. So you can actually take the log base 10, or you can take the natural log with a base of e of both sides, because if I do something to both sides, it doesn't change the value of anything. So mathematically, we can do that. I want to make this base of 2 raised to the x and this base of 3 raised to the x minus 1 the argument of those logs, okay? So I'm going to do log of base 10. So I'm going to take the log of the both sides. So this is now going to be log of 2 to the x equals log of 3 to the x minus 1. Now that we have that as our argument, we can apply the power property and move that exponent out in front as a coefficient. So this is going to be x times log of 2 is equal to x minus 1 times log of 3. Now, we know that we cannot distribute log or natural log to an argument. However, what we're seeing on this right-hand side is we're seeing the log of 3 times x minus 1. Log of 3 is a number. That's 10 raised to some power equals 3. That's a decimal, but it's a number, right? So we can distribute log of 3 to the x and to the negative 1. So that we're going to do that. So we're going to get x log of 2 is equal to x log of 3, and then minus 1, which is just going to be minus log of 3. Now our goal is to solve for x. So what we're going to do is we're going to get everything that has an x in it to one side, everything else on the other. So I'm going to subtract over that x log of 3. So I have x log 2 minus x log 3 is equal to negative log of 3. Similar to solving for the inverse of those rational functions, whenever we have every term with an x on one side, what do they have in common? They all have an x. Factor it out. And then because we want to get x by itself, we can divide by that and get x to be negative log 3 divided by log of 2 divided by log of 3. This is your exact answer. Now, there's multiple ways to write this as an answer. You know, in your denominator, you could write that as log of 2/3. You know, in the numerator, you could move that negative 1 out in front as an exponent. So 3 to the negative 1 power would be log of 1/3. You could rewrite that as log of 1/3 divided by 2/3, whatever. There's multiple ways of writing that correct answer, but I'm not too concerned about that. I'm just concerned about you solving for x. Like I said, this is a numerical value. You could plug that into the calculator and get some decimal approximation, but we want the exact value of x here. So this is all that we want. If you are solving and you get some other form of your answer and you're not quite sure if it's the same thing as what I got, put it into the calculator and see if the decimal approximations are the same. If they are, then you're good. Okay, so let's do it again here for example 2. I cannot rewrite my bases to be the same, so I'm going to take the log of both sides, or the natural log, it doesn't matter. And so now I'm going to apply that power property. Now I'm going to distribute the log of 3 to the x and the 2 and distribute the log of 7 to the x and the negative 1. Now I'm going to get everything with x's on one side and everything else on the other side. So now it's going to look like this. And we want to solve for x, so factor it out. And then divide by the leftover, and we get x by itself. It's an ugly number. It's a lot of writing, but it's not hard to solve once you get it in the right setup. Okay, and again, this is just one way of writing that answer. You're more than welcome to condense and rewrite it a different way, but you don't have to. Like I said, our goal is to solve for x. That's what we did. This is the exact value. Okay, so this is just kind of adding another method of solving these exponential functions whenever you can't make your bases the same. Okay, now we're going to see things like example 3. E to the 2x minus e to the x minus 6 equals 0. When you look at something like that, I'm hoping in your head you're thinking, man, that looks like a quadratic, but it's not really quadratic, but it looks like it. Well, it actually is a quadratic. If you can't notice it, let's replace e to the x with something. So I'm going to let y equal e to the x. So that would be y squared minus y minus 6 equals 0. Now, hopefully you can see that this is a quadratic that is factorable. Factors of negative 6 that add up to negative 1 would be a negative 3 and a positive 2. So that means y is equal to 3 and y is equal to negative 2. But I don't want to solve for y, I want to solve for x. So I'm going to do my substitution again and say e to the x is equal to 3 and e to the x is negative 2. Well, to solve for x here, I'm going to have to rewrite this as a natural log. Rewrite it in log form. If my base is e, that's the natural log of 3 is equal to x, which is one of my answers. And then over here, the natural log of negative 2 is equal to x. Well, this is an extraneous solution because we know our arguments cannot be negative. So my only answer for this quadratic would be x is equal to the natural log of 3. So a lot of these, like I said, are going to be solved with factoring or solving a quadratic. It's just sometimes that quadratic is hidden in the problem, and we have to do a couple things before we can see it being a quadratic and then solve that. Example 4 looks really ugly, but if you see exactly what you're dealing with, it's not so hard to solve. So in this one, I need you to understand that on the left-hand side, 2 is a base, and it's being raised to a power of 2 divided by log base 5 of x, okay? So if you need to rewrite that kind of as 2 raised to the 2 divided by log base 5 of x, maybe that'll help you. Okay, so 2 is the base on the left-hand side, and that's going to equal 1 over 16. Well, we can write 1 over 16 as a base of 2. 2 to the 4th power is 16, so 1 over that is going to be 2 to the negative 4 power. Well, now that my bases are the same, I can set my exponents equal to each other. How do I solve for x? Well, I can multiply both sides by the log base 5 of x. Get to the x, divide by that negative 4, so we're isolating the log. 2 divided by negative 4 is the same thing as negative 1/2. And now I'm going to write this in exponential form. Base of 5 raised to the negative 1/2 power is equal to x. Remember what a negative power does and what a fraction does. A negative is going to reciprocate, a fraction takes the root, right? So this is now 1 over 5 to raise to the 1/2, which is the square root of 5. We know we don't leave radicals in the denominator, so to rationalize this, I would multiply the top and the bottom by the square root of 5 and get the square root of 5 over 5 as my value of x, okay? This is not typically wrong. However, you're never going to see that as a final answer in pre-cal or calculus or on a SAT or ACT type problem, right? You're never going to see that as an answer choice. That's never going to be a final answer. It's not technically wrong to leave it as 1 over the square root of 5, but I would get in the habit of rationalizing, just so you know that those two things are equivalent. Okay. Okay, so example 5. So we have 5 to the x is equal to 3 times 5 to the negative x plus 2. So for this one, I know it looks really ugly and you may be thinking, I don't even know where to begin. Well, for me personally, I see 5 to the x and I see a 5 to the negative x. So kind of a red flag's going off in my brain. Well, how do I apply a negative exponent? A negative exponent is going to reciprocate. So if I rewrite this as 5 to the x is equal to 3 times, this is 1 over 5 to the x, right, plus 2. The only thing being raised to that negative x power was the 5, not the 3. Okay, so we're here now. Another way to write this, if you want, would be 3 divided by 5 to the x. And that might actually help our next step. We don't want to work with a fraction. So how do we get rid of it? We multiply by the denominator. Well, I can't just multiply this one term by the denominator and keep it an equivalent equation. So I'm going to multiply everything by that denominator of 5 to the x. 5 to the x times 5 to the x is 5 to the x squared, or 5 to the 2x, because my bases are the same, so I add my exponents, equals 3 plus 2 times 5 to the x. Now, if I rearrange it, you may see 5 to the 2x minus 2 times 5 to the x minus 3 equals 0. Do you see the quadratic? If not, do another substitution. Let y or u or a or b or whatever, don't use x, let y equal 5 to the x. So that means now I have y squared minus 2y minus 3 equals 0. Hopefully now you can see this as a quadratic and you can easily factor that. Factors of negative 3 that add up to negative 2, negative 3, positive 1. So y is equal to 3 and y is equal to negative 1. But I don't want to solve for y, I want to solve for x. So I'm going to do my substitution again. Oops. You know, I write big. All right, so we're here. Okay, I don't want y, I want 5 to the x is equal to 3, and 5 to the x is equal to negative 1. In order to solve for x, which is the exponent, I need to rewrite this in log form. So log base 5 of 3 is equal to x. Log base 5 of negative 1 is equal to x. Not a solution because I have a negative argument, so log base 5 of 3 is my only value of x. Okay, this is a really hard problem if you just look at it, but if you take it step by step and know that, oh, that 5 to the x, something's in common there, and then rewrite it as a quadratic. The quadratic was not hard to solve. Plugging it in and, you know, these last couple steps, that's not hard to solve. It's that first part of recognizing it, okay? Hidden quadratics. Example 6 is also a hidden quadratic. I see 4 to the x and 2 to the x, and something catches my brain about that because I know I can rewrite 4 as a base of 2. 4 is 2 squared. So if I rewrite this as 2 squared to the x, that becomes 2 to the 2x minus 2 to the x equals 12. That's a quadratic. 2 to the x, let's say I set y is equal to 2 to the x, so now I have y squared minus y. I'm going to go ahead and subtract that 12 over, and that equals 0. Y minus 4, y plus 3, so y equals 4, and y equals negative 3. Replace that with 2 to the x. And then to solve for that variable in the exponent, we're going to rewrite this as a log. Extraneous solution because the argument is negative. Now over here, you technically didn't have to, because the numbers are easy, you shouldn't have to rewrite this as a log in order to solve for x, because you should be able to look right here and know that 2 to the what power is equal to 4? X is equal to 2. Okay? So you have this new method of taking the log on both sides when you can't write your bases to be the same number. And then you have these kind of practice problems of kind of manipulating these quadratics and solving these quadratics when they are using exponentials. Okay, the second page is really just a review. It's more applications. This time we're doing the algebra and solving for those exponents using logs rather than putting it into our y equals and letting the calculator solve it and give us that decimal approximation. For these, we actually want to leave it in exact form. At the end, we can plug it into the calculator and get a decimal approximation just to see if it's a realistic answer and kind of check ourselves there. But we're going to use the algebra to solve with logs. So you have your compound interest, you have your continual compound interest, half-life, and obviously you would know double growth and then your yearly just growth or decay rate. So it says the half-life of a radioactive element is 40 days. So we already know we're using the half-life formula. So some amount after a certain amount of time is equal to the initial amount, base of 1/2 raised to the time divided by h. Remember, h is the half-life of that element, bacteria, whatever we're talking about, virus, whatever. It says if I start with 200 grams, so there's my initial amount. I know I'm doing a half-life, and it says the half-life was 40 days, so some time divided by 40. After how many days would you be left with 75 grams? So that is the amount after a certain amount of time that we are trying to solve for. So our goal is to solve for that variable of t, which is in the exponent. So I know I need to do a log to get there. Before I can do that, I want to isolate the term that has the exponent. So I'm going to divide by 200. And then that's going to equal my 1/2, base of 1/2, raised to the t divided by 40. Now I can rewrite this as a log. My base is 1/2. My argument is the 75 over 200. And then that's going to equal the exponent of t divided by 40. How do I get to the t? Multiply by 40 on both sides. 40 times log base 1/2 of 75 over 200 is equal to t. This is my answer. That is an exact answer for the time it's going to take to go from 200 to 75 grams of this element. Now, you could plug this into the calculator and get a decimal approximation and get about 56.6 days. And then remember, we can always check ourselves. If I start with 200 and the half-life is 40 days, 200, 40 days later, I'm at 100. 40 days later, which would be at 80 days, I'd be at 50 grams. Well, 75 is somewhere between 100 and 50, so it makes sense that between 40 days and 80 days, I have 56.6 days. So that is a good answer for me in my brain. Okay. Example 8, the number of bacteria in a culture is growing at a continuous rate. The number of bacteria increases from 600 to 800 in 5 hours. Okay, so let's think about that. 600 to 800, that's not a half-life, and that's not a double growth. That's actually tripling in size from 600 to 1800 in 5 hours. So we're not using a half-life formula, but we're using that model of it. So my initial amount is 600. I'm tripling in size every 5 hours. So something divided by 5. It says how many bacteria will there be after 12 hours? So I'm actually trying to find that amount after 12 hours. We actually are not solving for an exponent here. This is just straight up plug it into the calculator and get your answer, which is 8,380 bacteria are remaining, or we have, in 12 hours. Let's think about this. 600 to 1800 in every 5 hours. So I'm tripling in size. So 1800 times 3, and then that would be in 10 hours, and then times 3 again would be in 15 hours. So it makes sense that between that 10 and that 15 mark, you're getting those 12 hours, which is about 8,380 bacteria. Okay, so didn't even need a log for that one. Example 9, you deposit $5,000 in an account with 1.25 interest compounded continuously. So now we know we're using this formula right there. Okay, PERT. Sometimes we call that PERT, principal e to the RT, PERT. How long will it take for that account to have 5,550? Well, my initial amount is my principal, e is my base, raised to the rate as a decimal, so 0.0125 times the time is equal to the amount after that said time. So our goal is to solve for that exponent, so we are going to use a log, and because our base is e, we're going to be using a natural log. So I need to isolate the exponential term, so divide by 5,000. So 5,500 divided by 5,000 is going to be really 55 divided by 50, which we then can reduce some more to 11 over 10, if you want to write that. E to the 0.0125 times t. So now I'm going to rewrite this as a log. log base e is a natural log of, I'm going to write that as 11 over 10 is equal to 0.0125 times t. How do I get to that value of t? Divide by that 0.0125. So the natural log of 11 over 10, which is some number, divided by 0.1025 is equal to the time it takes to do that. That is the exact time. When we put that into the calculator and either do it, G-solve on the calculator with the graph, you're getting an approximation. That approximation would be about 7.6725 years, just to give you an idea, but this is the exact answer we were looking for, solving it algebraically without a calculator. That's what I would want. Okay. You're really done. Like example 7 and example 9 were really what we wanted to show you of solving for that exponent using logs now and not using that y equals in the calculator. But 10 and 11, we just put on there, we found interesting because these are actual real life examples of models that use log or natural log in the growth or decay model for that instance. Some things that involve log or natural log or the Richter scale, which is to measure earthquakes, right? And also the decibel. To get the decibel, how loud something is, it also uses a log. So if you haven't already in chemistry talked about something being acidic or basic based on its level of pH, that pH formula does involve a log. So if you haven't, like I said, already talked about that in chemistry, then here's a little heads up. So it says in chemistry, the formula for pH is equal to the negative log of the hydrogen ion concentration measured in moles per liter. If that pH level is less than 7, you should know it's acidic. If it's greater than 7, it's basic. So I tell you what the hydrogen ion concentration is for apple juice. So using this formula, we would want to determine if apple juice is acidic or basic. So we are literally just plugging it in. We are not like solving for anything like using logs. I just am showing you this because I found it, we found it to be interesting. So the pH level for apple juice is going to be negative log of that ion concentration is 0.0003. If I plug that into the calculator, I do get a value of 3.523. So that means that apple juice is acidic because it has a pH level less than 7. And then the other one, which I thought was so sweet, is how to convert dog years to human years in a more accurate way than what a lot of us just say, like, oh, take the dog's age and add 7 years to it. It's actually not the most accurate way to convert. So, which makes sense that you would think about a dog's life from puppy stage to adult stage is kind of exponential in regards to how a human ages. So, it uses actually the natural log. So it says the human years is equal to 16 times the natural log of the dog's age plus 31. So if we wanted to see what the human age would be of a 15-year-old dog, which as you probably know, a 15-year-old dog is really, really old and probably on its last leg, poor thing. That human age would be 16 times the natural log of 15 plus 31. Again, this is just plug and chug into the calculator, and that dog's age represented in human years would be about 74.329 years. Okay, so those two, like I said, were just kind of fun. 7 and 9 are where you're solving for that exponent algebraically using what we know now with logs. And then these, like I said, a little bit more challenging, kind of some hidden factoring within those exponents and this new method of solving when you can't put your bases as the same number. Go do your practice. See you later.